Assalamu alaikum dear student. I hope everybody will be fine. Today we will discuss the green theorem. To move over the green theorem, firstly we have to understand that if we integrate the function, particular type of a function, along the closed region R, it will be the same as if we integrate the function along the closed curve C. Along the region R and along the closed curve C, both will be the same. Now dear students, he says that let R be a simply connected region in the xy plane bounded by the closed curve C. Let's say this is the closed curve C and this is the region bounded by the closed curve C. And if m and n are the continuous function of xy having continuous derivative, then if the function has continuous derivative, then we can interchange its derivative with respect to x and with respect to y. So I can also write it as dy dx or dx dy. It doesn't affect. So dear student, where C be considered as the anti-clockwise, not clockwise. If it is clockwise, we have to change its direction, so minus sign will be there. Now the question comes here, simply connected region. What is simply connected region? As we have studied in the complex number, simply connected domain and multiply connected domain. If the domain does not intersect it at any intermediate point, then it is the closed domain, in closed curve. So it will be the same, the closed, or it contains no point over which the given function is undefined or is not differentiable. So for every point in the region R, there is no point over which m and n are ceases to be differentiable. It means इसमें कोई ऐसा पॉइंट नहीं है जहाँ पे फंक्शन जो है तो m और n फंक्शन है वो डिफरेंशिएबल ना हो. एवरी पॉइंट के ऊपर फंक्शन जो है वो डिफरेंशिएबल है. तो डियर स्टूडेंट वो कह रहा है कि लेट्स से m and n आर द continuous function of m and n would be the function of x and y, and they are differentiable function and their derivative are also continuous. Then we can integrate this m dx plus n dy along the closed curve C, or taking partial derivative of n with respect to x and m with respect to y. Their subtraction is also integrable over the region R. So when we integrate over the region R, we have double integration. It will be same as when we integrate along the closed curve C. So now we do its examples. Let's say m be a function of x and y defined as xy plus y square, and n be a function of x and y defined as x square, R be the region in xy plane bounded by y equal to x square and y equal to x. Then he says verify Green's. So dear student, the region is defined as y equal to x line is defined as this, and y equal to x square is a graph of parabolic shape. So this point is origin where they intersect, and this point is 1 1 where the straight line and the parabola intersect. So this region is bounded R this one and this one. Let's say this is C1, let's say this is C2, and the region between this we say R. This is region bounded by the closed curve, and this closed curve is obtained by C1 and C2. So we have to verify Green theorem. So we know that by Green theorem integration along the closed curve C, then mdx and dy must be same when we integrate along the closed region R to nx my dx dy. So firstly we consider left hand side, then to right hand side. This is your question and this is your answer. So dear student, firstly we solve this one, mdx and dy. See, what is m? xy plus y square dx and x square dy. So we know, let's say this is 1 and where integration along the closed curve C is defined as the integration separately by C1 and C2, because the closed curve C is obtained by adding the two curves C1 and by the joining of two curves C1 and C2. So I split my integration along C1 and C2. Along the curve C1, the equation is y equal to x square, so dy is 2x dx. And along the curve C2, and for the curve C2 we have y equal to x, so dy equal to dx. So dear student, it means I can write along the curve C1 xy plus y square dx x square dy plus along the curve C2 xy y square dx plus x square dy this is integral along the closed curve C. So what is dx? Okay, what is y? Y is x square, x square whole square, and dx. And range of C1 is from 0 to 1. And for the curve C2, we again have plus x square. What is dy? Dy is 2x dx. From 0 to 1. And for the curve C2, y is x, x square dy. Dy is dx. It is again from one to 0. Because C2 curve is moving from for this one direction, C2 curve having this direction, so it means from 1 to 0. Now dear student, we can write here from 0 to 1 x cube plus x4 2x cube dx from 1 to 0 2x square and 3x square dx. Here we can see that 0 to 1 3x cube x4 dx 1 to 0 3x square dx, and we can write here 3 by 4 x4 1 over 5 x5 plus x cube. This is from 0 to 1 and this is from 1 to 0. So I can write here 3 over 4 1 over 5 minus 1. So I can write here 20 15 plus 4 minus 1, which is 19 by 20 minus 1 minus 1 by 20. This is the left hand side. Now we try to find the right hand side for the region R. So dear student, I can write here for the region R, M is defined as xy plus y square and n is defined as x square. So partial derivative of n with respect to x is 2x, and derivative of y with m with respect to y is x plus 2y dx dy. So the question arises here, what would be the limit for the closed region R? 2x mean x minus 2y dx dy. It is up to us that if we want to interchange dy dx, we can easily, because the derivative are continuous. If derivative are not continuous, then we cannot interchange. We have already studied it in the vector analysis. तो डियर स्टूडेंट, यहाँ पर जो रीजन आर है उसके लिए एक्स की लिमिट देखिए क्या है. ओके, जो एक्सटर्नल डिफरेंशियल है, फॉर द एक्सटर्नल वी ट्राई टू राइट डाउन एक्स इन टर्म ऑफ द इंटरनल वेरिएबल. तो हियर द इंटरनल वेरिएबल इज डी वाई, so we can write it as okay, we know that in the xy plane x moves horizontally and y move vertically. So from C1 to C2 I have this direction. I have this direction. So it means from this is C1, this is C2, and from C1 to C2 I have this direction. So it means this curve is y equal to x square and this curve is y equal to x. So dear student, I can write here from y equal to x square. So x would be square root y to y, because from here x is square root y, and dy is for the value of y we have range from 1 to 0 because dear student, from we are moving from C1 to C2. So C1 is starting from here and ending here, and C2 starting from this one point and ending at this point. So range of y would be from this one to this one vertically, and for the x-axis we have to move horizontally. We are moving from C1 to C2, so we have to take a start from x square and have to end at y equal to x. So from conversion we can get here x is equal to square root y and x is equal to y. So different from 1 to 0, x square by 2 minus 2yx square root y to y dy. And from here I can write 1 to 0 y square by 2 2y square minus time y by 2 minus 2y 3/2 dy. Happy with it? So here we can write (1 to 0) minus 3/2 y square minus y/2 plus 2y 3/2 dy. So minus 1/2 y cube 1 to 0 y 2/4 1 to 0 plus 2 5/2 5/2 from 1 to 0. Minus 1/2 minus 1 minus 1/4 4/5 minus 1 1/2 1/4 minus 4/5 3/4 minus 4/5 20 16 minus 1/20, which is same as when we integrate it along the curve C. So Green's theorem is verified here. Now dear student, we try to solve it with an alternative method. So it is you can also choose one of the method that you like. Let's say we have to integrate along the curve R, partial n by partial x, partial n by partial y, dy dx. First, in the previous method we integrate with respect to dx and dy, and here I am integrating with respect to dy and then dx. M is xy plus y square and n is x square, so 2x dy dx. What is y? We have to choose y vertically and x horizontally. So from C1 to C2 I will choose y. So this curve is y equal to x square and this is y equal to x. So vertically I can choose from x square to x, and what is x? From 0 to 1. This is x and this is y. Zero to 1. This one point is to be noted here. It's the limit for the external differential must be the constant. Means you are starting from x is equal to 0 to 1. But for the internal differential, you have to use limit variable from xk to x. Okay. So dear student, xy minus y square from x square to x dx and I can write here x square minus x square x cube minus x4 dx, which is same as 0 to 1 x4 minus x cube dx x 5 by 5 x 4 by 4 0 to 1 1 over 5 1 over 4 20 minus 1 by 20. Whatever the differential you want to choose earlier and the later, it is up to you. You can integrate it with respect to x first and then y, or then firstly with the y and then with respect to the x, which is the same. And we have also seen here the double integration can be evaluated with the help of the closed curve C using the single integral. So this is the end of the first example. Now I am sharing you with this. I am sharing you this second example. Just in this solved problem number 21, he says verify Green theorem for m equal y minus sin x and n equal cos x, where the closed region C, where the closed curve C is defined as pi by 2 1, pi by 2 0, and the origin 0 0. The direction is mentioned. Let's say this is curve C1, this is C2, and this is C3. So I try to solve it. So he says verify Green's theorem. So dear student, firstly I consider along the closed curve C m dx and dy, and I can integrate it along the curve C1, C2 and C3. So to go over there, it is better to firstly write what is m, y minus sin x and cos x dy. So dear student, I can write here yes, I can integrate it along the curve C1, C2 and C3. So dear student, along the curve C1 I can write okay. For C1, the equation of the C1 is y equal to 0 and equation of C2 is x equal to pi by 2, because this is parallel to the y-axis, it is parallel to the x-axis. And for curve C3, so 2 points are given and the equation of line passing through the origin. So y equal to mx would be the equation. So y equal to mx, and m is defined as 1 minus 0, pi by 2 minus 0, which is 2 by pi. So it means the equation would be y equal to 2 over pi x. So dear student, I can write here close integration along the closed curve C and integration along the curve 1 y equal to 0. It means dy would be 0, here dx would be 0, and here dy equal to 2 over pi dx. So dear student, I can write here along the curve C1 y is 0, so dy is 0. It will be finished, and y is 0, so I have minus sin x dx, and limit of C1 is from 0 to pi by 2. So I can write here 0 to pi by 2. For the curve C2, I can write x is pi by 2. So dx is 0, the whole factor is 0, and x is pi by 2, so at pi by 2 cos is 0. It means along the curve C2 there is nothing. And for the curve C3, y is 2 over pi x, 2 over pi x sin x dx plus cos y what is y? 2 over pi x, okay, sorry, cos x, and dy is 2 over pi dx. So dear student, I can write here cos x from 0 to pi by 2. And what about C3? C3 in this direction, so it means from here to here, from pi by 2 to 0. So 2 over pi x square by 2 plus cos x plus sin x 2 over pi and limit from pi by 2 to 0. This is minus 1 plus 0 1, okay, 1 minus this 2 is balance, so pi square by 4 at pi by 2 it is 0 and pi by 2 it is 1, so 2 over pi. So dear student, I can write from here minus 1 plus 1 minus pi by 4 minus 2 by pi. So I can write it 4 pi square plus 8 minus time pi square plus 8. Okay dear student, now we move toward the another side for the region bounded by the closed curve, mean integrating double integral along the closed region R. What is n? N is cos x and m is y minus sin x. So I can write from here nx is minus sin x and my is 1.